In this video, we are going to have the proof of theorem 5.3.2 given as an Hustain. If f of x, which is a member of fx, is of degree n, then there is an extension e of f in which f of x has n roots and degree of e over f is n factorial. So actually, in Hustain, you would have mentioned that this theorem is a corollary to this corollary, but the proof is somewhat bigger than proof usually given under any statement in a corollary. This is given as theorem itself. Now, in the previous video, we had this. If f of x is of degree n, then there is an extension e of f in which f of x has a root, and not only that, degree of e over f is less than or equal to degree of f of x in E. So this concept that we'll be using in proving this theorem. Now the proof is by induction on degree of f of x. If degree of f of x is 1, then it should be f of x should be a linear expression like this. Then obviously minus beta by alpha is the root of this. And this is a member of capital F, very obvious. Alpha and beta are there in F. F is a field, so it should be a member of F. Now, as every field is an extension of itself, degree of F over F is 1, and the theorem follows. See, we need to have the degree of E over F to be less than or equal to n factorial. Here n is 1, and in the place of E you have F, so it is equal to 1, and the degree is also 1. Now we have the induction hypothesis. This is base case, and here we have the induction hypothesis. Assume the theorem to be true for all polynomials of degree less than n, and we shall assume that degree of f of x to be n. Then by the above corollary, there is an extension E naught of f such that f of x has a root, say alpha, in E naught. Then by factor theorem, we can write, because alpha is a root, x minus alpha becomes a factor. So f of x is equal to x minus alpha into g of x, where g of x belongs to E naught of x. Then this f of x being a member of fx and f contained in E naught is considered to be an extension. So this f of x should be an E naught of x. So, and the degree of g of x is n minus 1. This is of degree n, this is of degree 1. So a g of x should be of degree n minus 1. Therefore, by induction hypothesis, there is an extension E of E naught such that degree of E over E naught is less than or equal to n minus 1 factorial. Because g of x is of degree n minus 1, we have this to be less than or equal to n minus 1 factorial. And g of x has n minus 1 roots. That's by our hypothesis. So, clubbing these two, we want to have the theorem to be true for f of x. So since f of x is of degree, by the above corollary, degree of E naught over f. This is degree of E naught over f to be less than or equal to degree of f of x, which is n. Now what we have is, you have f base field, then you had an extension E naught, then you had an extension E. So degree of E over f should be degree of E over E naught into degree of E naught over f, which was established in the first section itself. That is in section 5.1. So this we know to be of degree n minus 1 factorial, and this to be of degree n. So you have degree of E over f to be less than or equal to n factorial. Now since f of x has a root alpha naught in E naught, and E naught is contained in E, f of x has a root in E. And as the n minus 1 roots of g of x in E, these are all, these roots are in E, being written as f of x is written as x minus alpha into g of x. F of x is written as f of x is already written as x minus alpha into g of x. So the roots of f of x are one from this, namely alpha, the other should be from g of x. So they are already in E, and this one is in E naught, but that is contained in E. So the whole lot, that is alpha and these roots, this is 1 and this is n minus 1 roots. So you have all of them, namely totally n roots in E. So we have all the n roots of f of x in E because of this. So and E is an extension of f. So we have established that whenever we are given f of x to be of degree, and then we can always find an extension, E of f in which f of x has n roots and degree of E over f is less than or equal to n factorial. Now in the next videos, we will have the proof of uniqueness of the splitting field, for which few lemmas and theorem like prerequisites we shall have them. But the entire prerequisite, if you consider, it will take more time. So we'll split the videos, and then finally we will have the proof of uniqueness of splitting field, which is the main aim of this section. Thank you.